thank you for the introduction, and also thanks a lot to all the organizers for inviting me and for making this conference happen. Well, I'm also missing the actual personal interaction a lot, and I hope I will be there next time to compensate for that. And I would also like to thank the organizers for recording all the talks. I know myself that, you know, with all the homeschooling and all the things that are happening these days, it's sometimes difficult to attend a conference the whole time. Or also the people who are in a different time zone should have the opportunity to watch the talks later. So thanks a lot for doing that. And I would, in that respect, I would also ask everybody who has questions later, who may watch this talk later, please do send me an email if you have any questions or comments. Okay, so what I'm going to talk about today is spacetime convergence for product spacetimes. And the main underlying idea why we studied this, so this is joint work with Brian Allen, is that, oh, I have to change my screen now. Is the question of how can we understand convergence of Lorentzian manifolds? So here I've just written a sequence of Lorentzian manifolds. A manifold is a metric, and we want to understand how we can understand convergence to some limiting object. So there are several questions to ask. Well, what should the limiting object even be, and what is the right notion of convergence for that? And so there are important questions that we have to understand before we want to even understand what kind of setting we want to pick. And so the main question is, well, what kind of geometric properties do we even want to capture? So depending on that, one may use a different notion of convergence. And so this is then the second question. Well, what kind of a convergence makes sense for these geometric properties, and what should the limiting space be? And then for me also, it's important to ask the question, well, how can we all of this apply then to spacetimes in general relativity? And so these are the basic ideas that, or the basic questions that you should somehow keep in mind during my talk. I will not be able to answer all of them, but it's the basic idea of why we were interested in this problem in the first place. And the underlying work that I'm going to present is spacetime convergence via the null distance. So the null distance is a notion, so it's a metric introduced by Sermani and Vega in 2016. And Christina Sermani has also started to address questions that one can study using this some kind of a spacetime convergence. And then Brian and myself, we try to study the simplest kind of models using the null distance and the convergence for those, and those are word products. And in order to even study convergence in this setting, one first has to understand a few extra properties of these spaces and how they behave with respect to this null distance. And in my talk is set up as follows. I'll first talk a little bit about motivation from Riemannian geometry. So ideally, what would one obtain, or can one obtain using such ideas? Then we'll dive into metric approaches in Lorentzian geometry. We've already heard a little bit by Olaf Müller already on Tuesday, or was it Monday? I forgot. And then in the last part of the talk, I'm actually going to discuss the null distance and convergence with respect to the null distance. And so if we go in Riemannian geometry, how do we obtain a notion of metric convergence? Well, we have a Riemannian manifold. We pick a class of curves, piecewise smooth paths, with a reparametrization or parization for those curves. We can compute the arc lengths, and then the Riemannian distance is just defined as the infimum lengths of all paths between two given points. And it is well known that this distance function gives us an intrinsic metric that induces the manifold topology. And a lot of additional properties we know as well. So why is this notion of a metric so important and so nice? Well, one is the first important result is the Hopf-Rinoff theorem is that relating geodesic completeness to metric completeness. This is a very nice result, I think. The other result is that we can actually study how close two Riemannian manifolds are, but not in terms of, but they don't need to be diffeomorphic, so just as metric spaces. And this goes back to the notion, using the notion of Gromov-Hausdorff convergence. So in this setting, we can study how close two Riemannian manifolds are as metric spaces. And there's another more recent version of convergence, which is the Semani-Weyner intrinsic flat convergence, where we not just have a metric space structure, but also an integral current. And you can think of an integral current for submanifolds just as integration over n-forms. So it's related to volumes. And for that, of course, the manifold also needs to have an orientation. So I will just give quite a very brief explanation of what these two notions of convergence mean, in case you've never seen this before. So the Gromov-Hausdorff distance is based on the Hausdorff distance. So you can imagine that you have two subsets in a metric space, and you would just want to compute how far they are away from each other, and you use this sub-inf. So you pick any points x and y from one of these sets each, and then you can compute this sub-inf, and the maximum of both interchanged gives you the Hausdorff distance. And then the Gromov-Hausdorff distance is essentially the version of the Hausdorff distance where you can just take any two metric spaces that you isometrically embed in a joint metric space, and then you take the infimum over all these possible isometric embeddings. So it's an isometric Hausdorff distance if you want. And so this gives you a notion of distance between two metric spaces. And the Gromov-Hausdorff distance is 0 if the two spaces are isometric. And the intrinsic flat distance is very much in the same way, but it adds a little bit more to that. So we also need a current. Initially, this was done in Euclidean space, and then later on it was translated to complete metric spaces by Ambrosi and Kirchheim. And in that way, you can view here in this picture submanifolds as integral as currents, and you can compute the distance between the two in terms of their volume, if you want. So this mass function m is essentially in this picture, it's just a volume, and you compute the difference in terms of how far they are apart volume-wise, if you want. And the intrinsic flat convergence is the intrinsic versions. Again, you can just take two integral current spaces that are embedded in a joint metric space, and that way you get an intrinsic notion, whereas initially the flat distance was again an extrinsic notion. And the intrinsic flat distance is 0 if the two spaces are current preserving isometric. So in a sense, we see that basically what we need is somewhat underlying metric structure, and then we can study these two notions of convergence, and of course others as well. And so what are the advantages of studying this kind of distances and convergence in Riemannian geometry? So it's well known that the Gromov-Hausdorff convergence works very well with lower sectional and Ricci curvature bounds. I'm not going into detail now. This was also mentioned earlier. On the other hand, the intrinsic flat convergence is a weaker notion of convergence. But in some cases, especially if the Ricci curvature is bounded from below by 0, then these limits may agree. And generally, what one can say, the basic idea of the intrinsic flat convergence is that they are not just compatible with Ricci curvature, but also with scalar curvature. And this has already been seen in the results that are related to the stability of the positive mass theorem. So there are several papers on that already. And one of them is the work by Leon Sormani, who showed that if the ADM mass converges to 0 of rotational symmetric asymptotically flat Riemannian manifolds, then in the intrinsic flat sense, the manifold converges to Euclidean space. Okay, this is just to give a brief idea of how these things can be used, these notions of convergence, and what results are already known that are somewhat related to general relativity. Okay, so now we try to do the same thing in Lorentzian geometry, and there are obvious problems there. So the first thing we want to do is we want to pick a space-time, so a time-oriented Lorentzian manifold. Again, we pick a class of curves, and now we take a piecewise smooth future-directed causal path, and we assign the arc lengths to them. And then the Lorentzian distance can be defined for any two, so non-zero for any 2 points that are causally related. And it's again the supremum of the arc length for this path. And the Lorentzian distance is actually a very useful concept, and a lot of things are known about it. So for instance, obviously, just by definition, it codes information about causality. We know that for instance, globally hyperbolic spacetimes, the Lorentzian distance is finite and continuous. However, one big drawback for our purpose is that it is not a metric. So it has some properties that are still useful, like the reverse triangle inequality, but that's not enough. And I should still say that the Lorentzian distance function has also been used in a sense to study metrics and metric convergence, and this is most prominent in the work of Noldus, who used this Lorentzian distance to define this strong metric. But we don't want to go this way, we want to go another way. I'm going to use in the rest of the talk this notion of a null distance of Sermani and Vega. And so the first thing I want to do is I want to explain, well, what is it and why is it useful? What is still known or not known about it, so that you get an idea of what this even is. So again, we start with a space-time. And on top of that, we also need to have a time function. And for the class of curves, we don't just take the future-directed curves, but we take a class of paths that are piecewise causal, and they can go up and down. So they can be future and past directed on their pieces, as you can see here in the picture. And then the idea is that you can compute the lengths of such a broken path using the time function. So you just compute the differences in their time between these pieces, and then you add them up. And this gives you the null length of such a path. And then the null distance is defined as the infimum over all these null lengths. And so you can see somehow the basic idea is, among all these definitions of distance, has always been the same. We needed some kind of a basic geometric structure, and then we needed a class of curves and the lengths, and then either by infimum or supremum we can define a distance. And so this is how the null distance is constructed. And of course, the first question that you want to ask, well, is it a metric, right? That's what we want. And so you see that in general, so even if you use a generalized time function, already you get a pseudometric. And whether it is a metric or not, that depends crucially on how good your time function is. And Sermani Vega have already studied this in detail for what kind of time functions you can expect it to obtain a metric. And indeed, you see, for instance, for these locally anti-Lipschitz time functions, you get a length metric. And there are some additional basic properties that I have here written down. So, of course, it then uses the manifold topology. Because the causal paths are conformally invariant, and so is the null distance. We have this scaling, and we have also this relation to causality, that if 2 points are causally related, then the null distance is just a difference in their time. And moreover, it is bounded on causal diamonds. So this is just a selection of some of these properties. And now I want to say a little bit more about the choice of the time function, because you may say, well, this is maybe very difficult to actually, get a meaningful null distance if I have a bad choice of a time function. And this is indeed, you have to be a little bit careful. But I want to also argue now that it's not too difficult to make a good choice. Okay. So the first thing that you observe is that, well, you can very easily make a bad choice. So for instance, if you don't use t as your time function in Minkowski space, but t to the power 3, then this null distance is not even definite, because the points at t equals 0 hypersurface, they obviously don't have they don't have a good distance, so that well, they are not separated. However, how can you, so that's a bad choice, but how can you actually pick a good time function? Well, there are several cases that have already been studied, and so I want to say a little bit about that. So the first argument that I already said before is that you pick a time function that's locally anti-Lipschitz. So you have 2 points that are causally related, then you can somehow, the difference in the time should then be bounded from below by some kind of a distance on an open set. This means that's what the term local means. So if it's global, of course, I would leave out that set U. Then there are also special cases where one can use very well-known notions of time functions. So for instance, these if you have a spacetime that admits a regular cosmological time function that is a notion based on the Lorentzian distance, as it's written here, then it's a good idea to use that one. But not all spacetimes will have that. And then another idea for warp products, this is what we are going to use, is that you pick a time function that is somewhat related to this to the t, and but you can also slightly modify it, and you still get a useful time function in that sense. With this phi of t, where phi prime is greater than 0. And in our paper, we also showed that, in fact, on compact sets, these the null distances are then equivalent. And with my PhD student, I last year also, in relation to that, showed that more generally, if you take temporal functions, then you also get that the null distances are equivalent on compact sets. So there are several good choices that you can make, but of course, it depends on your situation. Okay, so there's another concept here that I want to briefly discuss is how does the null distance relate to causality? So the first thing that we observe is, and this is just immediately follows from the distance, if Q is in the causal future of P, then the null distance is just a difference in the time tau Q minus tau P. And the question one should ask, if one really wants to understand causality in terms of the null distance, is, well, when does the converse also hold? And so Sermani and Vega coined a notion of causality encoding for that scenario. And that just means that this is an equivalence, not just an implication. And then you can ask, well, when is this satisfied? And this is still an open problem in all generality, but for the case that we are interested in to study later, so for warp products, there's already known and that this holds. And this is again true if you choose a time function tau that is just a phi of t, with phi prime greater than 0. And it should be fairly obvious, but we have also studied some examples that show that if you remove points from your manifold, then this is a natural obstruction to obtain this property. And well, one can then in this context consider whether maybe this notion should be slightly adopted so that it kind of that it kind of fits better. So this is still a little bit open how generally this holds and whether it is the correct notion for the most general case. But as I said, for warp products, this is already established and holds. And so this is the case that we want to study. And another thing, so that I kind of argued in the beginning, that one of the first results that you have for Riemannian manifolds is that metric completeness is equivalent to geodesic completeness. Now, we don't really get that. There's no such obvious connection. But we can still understand completeness as a metric space. And what we showed that is if you pick a time function that is globally anti-Lipschitz with respect to a complete metric, so complete Riemannian metric, for instance, then the manifold with respect to the null distance is also a complete metric space. So there's a little bit understood about that already. And but you have to be still very careful what completeness means. So for instance, just because the space is complete, it does not even mean that the distance between 2 points is achieved. And there's a very simple example, actually also a warp product. where the light cone of this metric somehow approaches the light cone of Minkowski space at t equals 0. And of course, if you pick 2 points that are P and Q that are on this t equals 0 hypersurface, then the shortest path will be, well, the limit of the shortest path will be just the straight line, the horizontal line. But obviously, that's not a piecewise causal path anymore. Okay, so this is a little bit about completeness. Now I just want to kind of summarize this again and then move on to actually study the convergence. So what I try to argue so far is that, well, we have this notion of null distance, and a lot of basic properties have already been established by Salmani and Vega. What you need to pick is a good time function, but it's not too complicated to pick a time function. And in particular, in the case of four-product spacetimes, this is very well understood, and this concept of a null distance is a very rich notion, because it also includes this causality encoding property. And so the main aim, or main broad aim, is then to use this null distance to study geometric stability of spacetimes. And this is what we set out to do. I have to say the paper already was finished about 2 years ago, and just in January it was now published online. So, but now it's actually available already. Okay. So the first thing, if you want to study stability or convergence with respect to the null distance, we need to have the right structure. So we already know that the null distance in case of these warp products yields a useful metric space structure. And this is enough for Gromov-Hausdorff convergence. But if we want to compare it to other notions of convergence, this may not be enough. And the notion that we're very interested in was exactly this notion of intrinsic flat convergence. And for that, you also need an integral current space. And the first thing that we had to therefore do is to show that we actually have an integral current space as well. And then the second part was to understand spacetime convergence for warp products, which are best understood. And so the idea was that, well, if it works for warp products, it can also work in other cases. And we also wanted to study different scenarios, different kinds of convergence for the warping function, so that we understand what are the really most important most important outcomes or expected outcomes in such a setting. Okay, so but before I go into the warp products, let's just look at the examples and look at what exactly the null distance actually looks like. And so you can just take a Lorentzian product, minus dt squared plus sigma, where sigma is some Riemannian manifold, Riemannian metric. Now I don't assume anything else at this point. And you can just define the null distance by just splitting up this the points in the t peak part and the p sigma part. And you will see that if the points are causally related, it's just a difference in their time. And if they're not causally related, then it's just a difference in the space, in the sigma, with respect to this Riemannian distance induced by the Riemannian metric sigma. And if you now move on to warp products, and we're a little bit more restricted with the warping function, so we said that it should in particular also be bounded from below and above. Well, you look at the Lorentzian metric with this warp product, then you can show that the null distance, again, if the 2 points are causally related, it's again just difference in their time. That's also what is always true. And if they're not causally related, then you can somehow estimate the null distance from above and below using your warping function. And so what you see is that now I already put in 2 different null distances. So one with respect to, if you would imagine the one before from the Lorentzian product where f equals 1, and just the f, warping function f, and then you can see that, well, you can estimate the null distance of the warp product with warping function f by those with just being the product, and the function itself, of course, and its bounds. And this result we could then use to show that we can induce an integral current on such a warp product. And so this is the main result, that, okay, now you have a little bit more assumptions. You take an interval and an orientable connected complete Riemannian manifold, a bounded warping function that is also bounded from above and below, so bounded away from zero. Otherwise it would become degenerate, so we don't want that. And then we can show that there exists a local integral current structure with respect to the null distance that you have in this case. And if the manifold is compact, then you get an integral current space. So these are slightly two different notions depending on whether you have compactness or not. Just like you have Gromov-Hausdorff convergence and pointed Gromov-Hausdorff convergence in the non-compact case, you have to distinguish these settings. And the basic idea of the proof is, I just wrote it down very briefly. So the first thing is, well, you know how to define an integral current structure on the Riemannian product. And then if you assume completeness, then you can have this Pythagorean formula, and you can use this Pythagorean formula to show that the identity is by Lipschitz with respect to the null distance now for the Lorentzian product. And that way you can push forward the Riemannian current to the Lorentzian product. And then you also have an identity that is by Lipschitz between the Lorentzian product and the warp product, just by this estimate that I shown before, and that way you can push forward the current again to the null distance associated to the warp product metric. So this is how you can show that you get this integral current space structure. And then what you could ask yourself is, well, this is kind of a sideline, and I will not explain all of this in detail now, but you know that if you have a complete Riemannian metric, and you look at warp products, then this is globally hyperbolic if and only if the Riemannian metric is complete. And so the next natural setting would be to study globally hyperbolic manifolds, which also have some kind of a completeness assumption in this case, in this way. Again, completeness now always in terms of metric completeness and not geodesic completeness. Of course, in the Riemannian it doesn't matter, but for the Lorentzian it makes a difference. And so this is a result that we obtain using this orthogonal splitting of Bernal and Sanchez, where we have this time function and we have these. Then we assume that we have these Cauchy hypersurfaces which have a complete metric, and the whole space as well is complete. That we can show that in this case we get a local integral current space. And again, if you assume completeness, you can obtain an integral current space. Okay, so I'm not going into detail with the proof of that because we are only interested in warp products, but I just want to say that you can actually obtain this integral current structure also in a more general case. Okay, so now we're coming already towards the end of actually studying the convergence. Now we have prepared the space. We can study two notions of convergence in principle. So we have not just, if we have a spacetime with a suitable time function and an associated null distance, we have first a metric space, and we have also a local, or depending on whether it's compact or not, an integral current space. And therefore we can study two very well-known notions for metric spaces, the Gromov-Hausdorff convergence and the intrinsic flat convergence. And we can do this for these spacetimes that we have, that we're interested in. So for the warp products. Okay. So here I'm just wrote a lot of technical assumptions. I'm not going to write them every time, but just to say that the convergence itself we actually studied in the compact case, because otherwise we would have to study the pointed convergence, and this will be just technically more complicated. But it doesn't say that it's not possible, but we just restrict it to the compact case to make it easier. So, so we assume a closed interval, and we assume now therefore a compact connected-oriented Riemannian manifold, and a sequence of warping functions that are continuous and uniformly bounded away from 0. And then we have, of course, the metric is these Lorentzian warp products. And what we showed is that if you assume that the warping functions converge uniformly, and therefore also the limiting warping function will be continuous, then the warp products with the corresponding null distances converge in the uniform sense, in the Gromov-Hausdorff sense, and in the Sermani-Wenger intrinsic flat sense, and the limit will always be the same. And this is a very elaborate proof, but I just want to give like some ideas of how it's built up and why it works. So okay, here's just a statement again, a little bit shortened. So the first thing, and this is actually the most difficult thing from in our paper, it takes up about 4 pages. The first thing you have to prove is pointwise convergence. And the idea is very simple, but you have to be very careful. So there's a lot of inequalities. So you assume, of course, that null distance is defined as the infimum over all null lengths of all these piecewise Procan paths. And so in order to get these estimates, you have to look at these kind of curves and estimate them in a useful way. I'm not going into the details of that. It's the basic idea is just that. And then you just have to very carefully do these computations. Okay, so the pointwise convergence. Then we also know that there is a subsequence which converges to some length metric space in the uniform Gromov-Hausdorff and Sermani intrinsic flat sense. And the reason for that is that we actually use a result of Huang Li and Sermani from 2017. And in order to apply that theorem, we need to prove these uniform bi-Lipschitz bounds. So you can see them here. You have to just estimate the null distances of some term of the sequence to some fixed other distance. And in this case, I just wrote 1, but it could be any other one as well. So, and to obtain these uniform bi-Lipschitz bounds, you again have to use these bi-Lipschitz estimates that I have written earlier already for these warp products. So this is very crucial that you can estimate this. And of course, what we also need in this setting is the assumption that we have these uniform bounds of the warping functions in our setting. So you have this uniform bi-Lipschitz bound, and then you just apply this theorem, and you get that you have that a subsequence converges to some length metric space. And then essentially the idea is to put these two things together. You already know the pointwise convergence to the right limit, but it's only pointwise. But you also know the convergence to some length metric space uniformly for a subsequence, and then you put these two things together, and you can show uniform Gromov-Hausdorff and Sermani-Wenger intrinsic flat convergence of the whole sequence to the metric space with the null distance of the limiting warping functions. Okay, this is just I'm not going to say anything about the details. Okay, so this is just the basic idea, and as I said, the pointwise convergence was also really difficult to establish. It's really very careful. You have to do it. And the question now is, well, when in this theorem we assume that the warping functions converge uniformly. So what would happen if you relax that property? And well, there are two things that can happen. Well, it works or it doesn't, right? So we have studied 3 examples in a lot of detail. There's different conversions of warping functions, mainly pointwise convergence, but some of them converge also in the LP sense for p greater or equal to 1. So this is a very general setting. So the first thing that you observed as well, if you don't assume non-uniform convergence, then everything can go wrong, basically. So one scenario is that that you have a convergence, but the limit is not the limit of the limiting warp product. Okay, and this can happen in particular if the null cones of the limiting warp product are more narrow than the sequences nearby. So you somehow restrict the class of admissible curves more and more, because the class of curves, of course, depends on the metric. which is not the case in Riemannian geometry, by the way. The class of curves is independent of the metric, and that makes everything a lot easier. And in this case, you always have to keep track not just of the distance, but also of the class of curves that is allowed. And so if you make the null cones in the limit too narrow, then this can be problematic if you don't assume uniform convergence. On the other hand, and this is a positive example, you don't always need uniform convergence. And so we also studied an example where the warping functions just converge pointwise. But in this case, as opposed to the first example, the null cones of the limiting space, they were wider than those of the sequence. And so you actually allow more curves in the limit, so you have no problem in that case, okay? So uniform convergence is not always necessary, but it shows you that somehow it depends on your limiting space in a sense. How is that related to your sequence? And then we also studied the case of a degenerate warp product. So you have, well, now I always assumed before that the warping functions are bounded away from 0. But of course, if you no longer assume uniform convergence, then, or if you don't impose these conditions, then the limiting space doesn't need to be Lorentzian. And so we still have the convergence, but not to a metric in the uniform sense. And in the Gromov-Hausdorff and Sermani-Wenger intrinsic flat sense, although these limits exist, they are actually different. So there is some kind of a collapse. So that also. So you can either have that the limits don't exist, or they're different, or they're not the ones that you expect. But on a more positive note, what I wrote at the very end, that example, again, is to show that, well, in some cases, you can actually still preserve this convergence. Even if you have only pointwise convergence with respect to the warping functions, you may still have uniform convergence of the null distances and all these other metric convergences as well. And in particular, again, the limits would agree or did agree in this example. And so, well, here are these examples where I just kind of showed that, well, maybe I'm not going to discuss this in detail now, but you can see here, this is the first example where the null cones are getting of the limiting warping function are in a sense more narrow, except at the t equals 0. And this leads to a problem. Then the second example was the one where the limits disagree. So where the warping function just becomes 0 in the limit. So this is this collapsing degenerate case. And the third example is the one where it actually works, where the limiting warping function, so that the warping function is always lower than the sequence, which means that the null cones are wider. And in that case, we don't actually have a problem. Okay, so now I would just like to summarize what I have said and kind of tell you, well, again, what is known and what is not known, and what I think are interesting results of this convergence and the notion of the null distance. So the first thing that we have seen is that, well, once we have a space-time with a suitable time function, one can obtain a null distance, and it is an intrinsic conformally invariant metric. And I wrote here just on most spacetimes, but of course what you only need is to have this suitable time function. And for instance, you can use cubic hyperbolic spacetimes. Then just by itself, by its definition, it's related to causality. But we only know, for instance, in the case of warp product and in some very special cases that it really is very closely related, so that it really is this kind of equivalent notion. And to understand this in more generalities is one of the, I would say, big open questions that was already mentioned in the first paper of Sermani and Vega. But even to understand it for more examples would already be an advantage. And again, the role of the time function. So if you choose so what you can expect from the results that I presented is also, this is maybe a rather vague formulation here, is that if you restrict or if you allow only a certain nice class of spacetimes of time functions, then you can of course expect that these null distances, they differ globally, but at least locally on compact sets they should be equivalent. And this is in a sense a little bit related to Riemannian geometry as well. So if you think of a manifold that you equip with two different Riemannian metrics, then also the distance functions, they will differ globally, but they will be equivalent on compact sets. And in a sense, the time function also, I think, should, if one can somehow narrow down this class of time functions that are allowed, should also, in the end, have such a property. So you pick two different time functions, like picking two different metrics if you want. So it is a restriction, but there is still something that is preserved. And the case where we have basically, where we already long knew all these properties are nice, is the case of warp products. And for those products, we prove that well, we have an integral current space, and then we can study the convergence of these warp products with their associated null distance, and we could show that they converge uniformly in the Gromov-Hausdorff sense and in the intrinsic flat sense to the same warping function, to the same limit. Namely, the limit is the null distance related to the warped product with a warping function of the limiting warping functions. Okay, complicated formulation. And this was always under the assumption, so that the theorem itself is always under the assumption that the warping functions converge uniformly. And with this kind of a hint to these three examples that we have studied, I just wanted to say that, well, in more generality, it's more complicated, but it's not completely hopeless. And it really depends a lot on the kind of situation you're in. And it should also a little bit point to what kind of scenarios can occur if you don't have warp products. Yeah, and with that, I would just like to thank you for your attention. And yeah, if you have any questions, please let me know.